All right, good afternoon, everyone. So let's talk about the midterm exam that's going to be here a week from today. Oh, wow, the room got really quiet suddenly. Yeah, so a week from today, midterm 1 will be here. The coverage of the midterm is up to including Unit 4, so none of this stuff on classification. So you have your homework and lab and quiz due today. Solutions will be posted soon. You can use all that material for studying. In addition, I will post a practice exam. Actually, it was the exam from last spring. And that you can also use for practice, that and the solutions. You're allowed to bring one 8.5 by 11 piece of paper with handwritten notes on both sides, so you can write down stuff. And I suggest that as a study technique to just go through all the note packets and write down what you think are like the most important things. When you do that, it just helps to organize everything in your brain. And even if, and you might find that just by doing that, you don't even need to refer to your note sheet later. On the other hand, if there's like some equation or something that you don't have memorized, that's another reason to do that. So any questions? Yeah. You can write on either side, both sides. Okay, great. Any other questions on the midterm? Okay, so the practice midterm is just one midterm. Midterm I give you next week may or may not be the same, easier, harder, right? They're always a little different. Do you have a question? No. Okay. All right. Any other questions? Okay. Yes. Question.
Will it be more similar to the homeworks or the systems?
Yeah. The midterm will be similar to the homeworks, and it won't cover any lab type material. So it's on the sort of derivation type material. To me, the quizzes cover the basic knowledge and the kind of questions you can answer in words, whereas the purpose of the homework and the exams is more like derivations, theoretical stuff. Great. Question?
So it would be like the quiz type of questions? Right?
So the quizzes are not usually that theoretical. The quizzes are like about information concepts. So I'm saying that the midterm exam is more like the homework. It's more like derivations, theory, things like that. Okay. Great. So let's get back to what we were talking about last time. So we're working on classification. We have some features X, and we want to figure out the binary label that corresponds to those features. So we're focusing on these linear methods, where what they do is they come up with this linear score Z, and then from Z, we do some sort of quantization to get the label. And the tricky problem here is how do you optimize the coefficients, the intercept and the weight terms. And we saw that if you optimize them with least squares, it doesn't work. So instead, we're talking about an alternative procedure here. And the main intuition here, I would say, is in this figure down here. This figure shows that we want some sort of approach that says when Z is more positive, the probability that y equals 1 increases. And so as Z goes to infinity, that probability goes to 1. Meanwhile, as Z gets smaller, more and more negative, that probability goes to 0. So that's the sort of model we want. And really, any kind of function that looks somewhat like this would probably work fine. And in fact, you can find there's lots of them that have been proposed. But this one, this logistic function here, is by far the most common and the most tractable as well. And it works pretty well, and I think that's why it's used so much. So that's kind of the high level why we're doing it, where this is coming from. And so these are the probabilistic models. So given the score Z, the probability that the label is 1 is this, or alternatively this, and the probability that the label is -1 is just 1 minus this, which is this. So now we have to figure out how to optimize the weights. And since we have these probabilistic models, we can use maximum likelihood estimation. And so we have this same procedure that we used previously for linear regression. There, we had an additive Gaussian model. Now, same procedure, but this logistic model. So we went through a bit of derivation, and we finally came up with these two optimization problems. So the first one is stated if y is plus or minus 1. The second one is if y is 0 or 1. Both are common versions of how the labels are given, and this is called the binary cross-entropy loss. So this is how we finally design our coefficients. This is not something that we can derive and write down an expression for the optimal B and W, but it is something that we can do computationally. These are convex functions, which means that you can find solutions without any trouble, and that's what scikit-learn does for us. All right, so that's sort of a summary of where we were. Oh, and then we also talked briefly about the fact that it's useful to add regularization, either a ridge style L2 or a lasso style L1. And in fact, some sort of regularization is necessary because if you use this technique with perfectly separable training data, you will actually find that without regularization, the coefficients will go off to infinity. You don't want that happening, so you put in maybe just a little bit of regularization like this with a very small alpha, and you find that it keeps the parameters bounded. And then we would use lasso or L1 if we want to do feature selection, if we want to figure out just a few features to use for prediction. And the way that we adjust the alphas is the same as always with cross-validation. Except instead of using like R2, we'll need to use another metric that's appropriate for classification. We'll talk a lot about those metrics today. Okay, so this is sort of the method. Any questions so far? Okay, so here's how you do it in scikit-learn. It's very similar to what we've seen until now. So you use, again, the linear model library, except now you use logistic regression. And the L2 regularization is included by default. So you have to tell it the value of the weight to use. Now it turns out that rather than specifying alpha, you specify alpha inverse, and they call it C. And so that means if you want alpha to be small, C needs to be large. So here we're specifying to use 1e5, 1 times 10 to the fifth, 100,000. And that's just a guess. That's just a large value that essentially doesn't add too much bias to the coefficients, but it keeps them finite. There is a default value you can read about. I can't remember exactly what the default is. It's probably also pretty big. So once you set up this, this object, so in this step we are doing the feature standardization. This function, preprocessing.scale, does exactly what the standard scaler does. It's just a different interface. You can read about it in the documentation if you like. Here is where we do the fitting. So we give it our training features, training labels, we do fit. Internally, it computes the B and W coefficients. And then if we want to do prediction, we do that, the dot predict. Here we're predicting our target labels. And finally, the most common way to measure the performance in classification is the accuracy, which you can see here. So this y hat equals y this produces a logical vector that equals 1 in all the locations where y hat equals y, and it returns 0 wherever y hat is not equal to y. So you have like a vector of 1s and 0s. If you take the mean of that vector, it basically gives you like an empirical estimate of the probability that these guys are equal. So that is what we call the accuracy. And in this case, for this breast cancer demo, the accuracy was almost 97%. So it's working pretty well. Okay, so that's how we use logistic regression. This shows you, this sort of just prints out a bunch of the internal parameters for logistic regression. So here you can see the value of C that we selected. Here you can see how the penalty defaults to L2. There's a lot of other stuff here. Like this tells you which numerical optimization algorithm is used to solve it. And the other things are not really that important. There's a tolerance on how precisely that algorithm solves it, like when does it stop trying. And we'll talk about some of these other things. This is an important thing we'll talk about very soon. Okay, so that's basically how we do logistic regression in scikit-learn. Pretty straightforward, very similar to linear regression. Okay. All right, any questions on this? Yes.
Does y in this go from 0 to 1 instead of -1 and 1?
So actually, if I remember, in this data set, for some reason, it was 2 and 4. So that doesn't bother scikit-learn at all. As far as I remember, I would have to look back at the demo, but I don't think we changed y to 0 and 1. But yeah, I don't know that you would need to. But it's a good question. Maybe I should check the demo. Yeah.
To do it by hand switching between two different values, would we just use like a separate variable transformation, like how you use -1 to 1 to go from that to like 0 to 1?
When you say by hand, what do you mean exactly?
So
Like
to go through the derivation.
like in Python?
Yeah. Or
Oh.
to actually get like the optimization equation. Yeah.
Oh, I see. Like this. So all you need is that your switching variable is either 0 or 1 for the two.
Okay.
So like here, it's 0 and 1 automatically. Here we had to change it this way. And so if it was 2 and 4 and you want to derive it, you would just come up with a little thing that is either 0 or 1 for 2 and 4. It's
Okay.
simple as that.
Thank you.
Sure. Great questions. Any other questions? Okay, good. So so we talked now, we got all the basics done for binary classification. Now let's move on to multi-class classification, which in this case means more than 2 classes. So what do we do then? So the way that we just formulate the problem, we say given some training data, same as before. The difference now is that our targets are going to be integers from 1 to k. So that's our assumption. And whereas before, there was 2 values, now there's k possible values. And these are categorical. These are not ordered in any way, like class 1 is not less than class 2 in any sense. They're just k different possibilities for the class. So maybe like you're trying to detect the species of an organism, so you have like cat, dog, cow, whatever, right? There's no ordering among those. They're just different classes. So that's the key point here, is that the target is categorical, whereas in regression, the target is ordinal. It's ordered. So just as before, we are going to design a classifier. Now, in this case, the classifier has to output a number in the integers from 1 through k. That's how we have to do it. And what we want, same as before, that the true target, the true label equals the predicted one with high probability. And we can also define decision regions in the same way as before. So for example, the kth decision region would mean the set of x for which our predictor outputs k. So here's an example where we have 10 different classes. This would be 2-dimensional features, x1 and x2, and you can see the decision regions that it came up with. The training data are plotted here. So like these are all the samples from one particular class. These red diamonds are another class. The red stars are another class, and so on. And you can see that it came up with some particular boundaries or classification regions to classify this data. So anything in this region here would be classified same as the pink triangles. So this would be an example because the classifier boundaries are not linear in X, this is a nonlinear classifier. All right, and just to kind of come back to this idea about categorical labels versus, or categorical targets versus ordinal targets. So there are cases where you can have a discrete target. Like, let's say you want to predict an Amazon rating that's either 1, 2, 3, 4, 5 stars. And so you might ask the question, is this a classification problem or is it a regression problem? So what do you think? Is that Amazon star rating, is that regression? How many people think it's regression? How many people think it's classification? Okay, so because those ratings, 1, 2, 3, 4, 5 stars, are ordered clearly, those are ordinal numbers, that's a regression problem. If you formulate it as classification, you could. You would find it doesn't work as well because you haven't told it that 1 star is less than 2 stars and 2 stars is less than 3 stars. So you're not giving it that extra information, which is really important. In this classification problem, it just thinks that they're all different. And so it kind of has less information to work with. So that's sort of a key point. So if the target is discrete but ordinal, it's probably a regression problem. Now, there are weird exceptions where you really have to think a little bit more deeply. And so the next homework assignment, which is not due until after the midterm week, so not due until 2 weeks from today. So I'll have a problem on there which gives you some slightly more tricky examples where you have to really think, is this going to be a classification problem or is it going to be a regression problem? Just so it's not always, discrete, or not always ordinal means classification, but if you think about it, I think you can usually figure out which approach to use. Okay, all right, so that's the idea. Now, how do we do multi-class classification? So there's many techniques out there, and it's also quite a bit more involved than the binary case. But like with the binary case, we're going to start with the simplest methods possible, and in fact, we're going to focus on doing multi-class using binary classifiers. Like, let's say we know how to do that. We know how to design these binary classifiers. Can we put a bunch of them together to do multi-class? So we're going to talk now about 2 approaches. The first is called one versus rest, or sometimes one versus all, and the second is one versus one. And so this is how it goes. So what you do in one versus rest is you look at the data in k different ways. So for each class little k, you think of the classification problem as in k versus not in k. So let me give you an example pictorially. So here we have 3 classes, red, green, blue. So one way I can think of this as a binary problem is I can say blue or not blue, right? And if I do that and treat that as a binary problem, and in particular like a binary linear classifier, I would be designing a decision boundary that looks somewhat like that, right? It's splitting the blue from the not blue classes. I can also then think of a green versus not green. That would be this boundary, and a red versus not red. Okay, so in each case, I'm using binary ideas. I've just come up with 3 different binary classifiers. So and that's what we're saying here. So like for each class, we can compute a separate score, zk, which is saying whether that sample X is in K or not in K. And then, once we have those 3 scores, or capital K scores, you just choose the index that maximizes it. So let me, again, come back to this. So let's say that I have a sample over here. I'll draw it over here. So if that's my sample, so one thing to remember is that if you just visually, the farther you go directly away from this boundary, the higher the score gets, right? Because along this boundary here, the score is 0. As I get deeper in this direction, I'm more and more confident it's blue, so my score increases. On the other hand, if I go this way, I'm more and more confident it's not blue, so my score z gets negative, more and more negative. So if I'm thinking about this point, you can see it's pretty far on the positive side of this blue classifier. So maybe that would mean like Z blue is large and positive. On the other hand, what about the green classifier? So for this point would be small and negative, right? Because it's on the other side. So it would be like Z green is less than 0. And for red, you can see it's very strongly negative. So Z red is much less than 0. So looking at these three Z's, I would choose the one that's the largest. So since out of these three, the blue one is the largest, I would choose blue. So that's what we're saying to do here. So that's how we're putting together three binary classifiers to do multi-class classification via the one versus rest or one versus all approach. Okay. So now you see that when you have three classes, you're actually going to be designing three separate linear models. Three separate linear models for this boundary. Very similar to in Lab 4, you were also designing like several separate predictors because you had vector value targets. So here we will also have vector value targets in a sense. Okay. Everybody good with one versus rest? Okay. This is also sometimes abbreviated OVR, one versus rest. Okay. The other approach, one versus one, it's not as common, but it does show up. We'll see it show up, I think, in the next unit. What you do is you consider each pair of classes. So in this case, when we have three classes, we have blue-green pair, blue-red pair, and green-red pair. We have three pairs. And so for each pair, what you do is you design a classifier that distinguishes or discriminates between those two pairs. And so now you're going to have, usually you have a bunch more classifiers. In this case, we have also three, but if I had more classes, I would have a lot more one versus one classifiers than one versus rest. So let me show you. So if we're doing blue versus green, we'd probably be building a model that's separating here, right? And then blue versus red would be one here, and then red versus green, another one here. So those would be the different classifiers that we're designing. And then the last step is to choose the class with the highest total score. So essentially, in this case, you're saying, let's look at, so this ZKL is if we're in K versus in L. And this is saying sum all of those over all the L's not equal to K. So if K is the blue one, I'm going to look at blue-green and blue-red. And I'm going to sum those scores and then maximize it. So this is just an alternate approach. At the end of the day, you still get a single answer. It's less common than one versus rest, so we won't really focus on it very much, but if it shows up, you know what it is. Okay, so those are two ways we can stitch together these binary classifiers to do more than binary classification. Okay, any questions here? All right, great. So, so now the slightly more difficult problem, though, is, well, how do we design the weights? How do we design for all these different classifiers now? This is going to be the one versus rest approach. How do we design all these weights and all these intercept terms? So now for each class K, we have a separate linear score. We have a separate ZK. So this is the score for class K. It's going to have a bias for class K or a intercept and weights for class K. And now this is the weights for class K and feature J. That's what KL means. And this score, remember, this tells us whether the sample X is in K or not in K. That's what it's telling us. And finally, we look at all those different scores and we pick the largest score, and with the index of that largest score, that is our winning class hypothesis. So the question now is, how do we design all these B's and W's? And essentially, there's two approaches. One is a very simple approach. The other approach is a more sophisticated approach that works better, but we're going to have to spend some time describing it. So here are the two approaches. And these are two approaches to train the coefficients. Both of them use this exactly. It's just a matter of how do you actually design the coefficients. So here the coefficients are these BKs and the WKs for all little k's between 1 and capital K, the number of classes. Okay, so the first approach is very simple to describe. You can describe it in one line. You just train K separate binary logistic regression models. So that's exactly what I described in pictures here. Like to design this model, I look at these two data sets and I design this B blue, W blue, and I'm done. Completely separately from that, I design this green model, B green, W green, and then I do the red one, B red, W red. So now I have independently, separately designed these BW things for the different Ks. Okay. Perhaps it's not super optimal or super sophisticated because I'm designing them in isolation. I'm not jointly designing them all together so that they work well together. So if you want to design them together, then we need to use a slightly more sophisticated model. And it's this thing called the softmax. And the softmax is, so this is the probabilistic model. And this is, in some sense, a direct generalization of the logistic model to multiple scores. So this is what it looks like. So you're saying, what is the probability that the label equals the integer k given my score vector z? And this is what it looks like. So here it's e raised to the power z sub k. So I'm using k to index into my vector of scores, and I'm just basically raising the kth score. I'm exponentiating the kth score. Now to explain the denominator, this is just the scaling factor you need so that these guys, if you sum over k, that they always equal 1. Because this is a property we need for this to be a valid probability mass function. If I think about this as a vector over k, or that's essentially a probability mass function, then that's what we need for it to be valid. Sum of the probabilities has to equal 1. Okay, so that's essentially where this is coming from. It's called the softmax because it has a certain property. It goes like this. So when you look at your z vector, if the largest term is much larger than all the other terms, then what happens is when you exponentiate that largest term, remember what happens if you put in a large variable inside an exponential? It gets giant, right? So this gets giant. And then when you look at all these terms here, okay, one of these terms is this guy, and all the other terms are going to be much, much smaller because the exponential has a way of just inflating the differences. So finally, you get that you have this divided by that plus a bunch of small terms, which is going to be approximately equal to 1 when this is your largest term, or when this is not your largest k, then this is a relatively small variable over a large variable plus small ones, which is approximately equal to 0. So in other words, it's like a soft maximum. This is an approximation. These values aren't exactly 1 and 0, but they're close. And in some sense, you can think of this as a one-hot coding, or this part is exactly a one-hot coding of this variable k-max. Remember, a one-hot coding is a vector where you have a bunch of zeros and a 1, where the location of the 1 is in the k-max position. Okay, so that's what this does, is it gives you an approximate one-hot coding of k-max. That's why it's called the softmax. Okay, so that's the approach. So now what we have to do next is we have to figure out how do we derive this negative log likelihood. And the main idea is is very similar to what we did with the binary case, just slightly different. So here's what we want to design. So we have a B vector. These are the intercepts for all the different K classes. And we have a weight matrix, which contains the weight vectors for the different classes. So our parameters now are the B vector, W matrix, and our likelihood is the probability of Y, which is, so this Y contains all our training targets, and these guys are all integers from 1 to capital K. Okay, and then here are training features as usual. So we know maximum likelihood just looks for the B and W to maximize this likelihood. Often we find that it's analytically simpler if we look at the negative log likelihood. So we know that when we take the log of this, so there's always going to be a product form here because we're always assuming that these Y's are IID, given all this other stuff. And so we have a product of scalar likelihoods, and when we take the log, that turns into a sum of log scalar likelihoods. Okay, so we have something of this form, and now the thing we have to do is think more carefully about this term. So here's what's kind of challenging, is that these yi's are integers, but similar to before, when we saw this in the binary case, depending on the value of the integer, the form of this changes. So now in particular, as I change this integer k, I'm actually extracting a different element from the z vector and exponentiating that. So that prevents me from easily writing down an equation for this. So there's a trick, which is to use one-hot coding of this label. So this is our integer label. Let's one-hot code that into a binary vector. Okay, so here, not boldface, integer. Here, boldface, vector. In particular, this is a one-hot coded vector, meaning it always has this sort of form. One of them is a 1, all the rest are zeros. And when this integer yi equals, when this equals little k, then it's the kth entry of this that is coming alive. Okay, so that's how you're coding it. You're saying, take this and use that to turn on the kth entry in my one-hot coded vector. Right? So the information contained in this integer and the information contained in this binary vector are the same. It's just a different way of writing it. Is that making sense? Okay, so now that we have that, here's another way to write this yik. So I, as usual, refers to the training index. K now refers to the class. So these yik variables, the ones inside here, are either 1 or 0, depending if k is yi or not. And now we can write this negative log term, this guy. This is the integer y. We can write this as follows. This is again using that switching variable trick, except it's like a multi-term switching variable. So these guys are either 0 or 1, and only one of them equals 1. And in particular, the one of these that equals 1 is whichever index has the value k. Okay, so when this guy has the value k, in other words, when this guy is k, we know the form that we want to insert. So this is that form, the exponential. That is this. So now we know that we're going to use the kth element of the score z whenever the corresponding k here is non-zero. So these are either 0 or 1. So when they're 0, kills this. The single one of them that's 1 makes this come alive. So I don't know if I explained that well, but essentially these are switching variables, but now one of them is on and all the rest are off. Okay, so that's how we went from this expression here where we had an integer yi to this one hot-coded thing that essentially turns on the correct term in the sum. Okay, and now the rest is very straightforward. We want to take the log of this fraction. So the log of the numerator is just zik. The log of the denominator is just, you can't really simplify it. And just one last simplification. So this is one term. We can't simplify that term, so that shows up here. But then we have this term over here. So this term, notice that I have a sum over k, and I have another term that does not depend on k at all. So I can essentially move this to the front if you like, and then I just have to evaluate this sum over k. But this is just summing together the entries in this one hot-coded vector. That will always equal 1, no matter what. So essentially this goes away, and the first term just becomes that one. So this is the final expression for this log likelihood, and we just plug that in, and we get, this is our, what we call cross entropy loss. This is the thing that we need to minimize to adjust all these B's and W's. So previously we saw the binary cross entropy loss. This is now just the non-binary or the generic cross entropy loss. Okay. Like in the binary case, this is a convex loss, which means even though we can't do it analytically, we can do this numerically with an algorithm. We can minimize this. Scikit-learn does it for us, just as before, just as in the binary case. And again, just as in the binary case, we will add L2 regularization or L1 regularization, whichever you want. And by default, scikit-learn adds L2. So works the same as before. In fact, the interface, everything is the same as before. It's just that this allows you to use labels where you have more than one label. More than one class, one possibility for each label. Sorry, more than two, more than binary. Okay, so that's the two approaches. And let me just come back here again and just review. So we have these two methods to design the coefficients. The first method trains each of these pairs separately without thinking about the others. And the second method that we just went over is more complicated, but it jointly trains all those B's and W's all together. And usually it works a bit better, but it takes longer to optimize. So there's a bit of a trade-off there. Sometimes you want to use one, sometimes you want to use the other, depending on how big your data is and so on. Okay, so that, that's essentially what I'm saying here. So this is, once again, I think this is the same thing we saw before, except now let's focus on this. So this line is where you tell it, in the multi-class case, which of the two methods you want to use to train. So when you choose OVR, it does the simple method where it trains each B-W pair independently of the others. On the other hand, if you select multi-class equals multinomial, then it does this MLR approach that we just described in these last few pages. So that is how you navigate this choice. Okay, so MLR usually has better performance, takes longer to train. Okay, so now we've covered binary logistic regression, multi-class logistic regression. We're done talking about these ways to design the coefficients. Now we're going to switch to ways to measure performance in classification. Are there any questions so far about anything here about MLR? Okay, great. So let's talk about performance metrics. Okay, so we're going to come back again to the binary case, simple case. And this is essentially shows you what can happen in binary classification. So here's the true label. Here is our prediction of it. So there's 4 cases it can happen. Either the true label was 1, prediction was 1, we call this a true positive, or the true was 0, prediction was 0, we call that a true negative. But then we have 2 different ways to make errors. Truth was 0, prediction was 1, that's a false positive, or the truth was 1, we predicted 0, that's a false negative. Okay, so false positives, sometimes people call them false alarms or false negatives, they call them misdetections. So in some applications, there's really not a lot of difference between these two types of mistakes you can make. So for example, if I'm sending you a stream of like millions of bits in a digital communication system, you don't really make a distinction between mistaking a 0 for 1 or 1 for 0. Those kind of errors are more or less the same because in those applications, they're very symmetric. On the other hand, in some other applications, there's a huge difference between these 2 types of negative errors. So let's consider cancer diagnosis. You take some tests to determine if you have cancer or not. The test is never perfect, so mistakes can happen, right? So on one hand, if you get a false positive, in that case, you're told you have cancer, but you don't. You know, you're depressed for a little bit, but it's not the end of the world because you're going to have more tests done, and eventually you'll figure out, oh, I don't actually have cancer. On the other hand, if you have a false negative, meaning you do have cancer, but the test said you don't, now you live your life. Meanwhile, the cancer grows inside you, and by the time that more symptoms appear, you take another test, it may be too late. Right? So in this cancer detection, these are very different. They have very different ramifications, and you really want to weight them differently. You don't want to say that they're equal. You want to think of them as different outcomes, different types of error. So that kind of motivates different ways to measure performance in classification. So the most common way is to measure the accuracy, and there you are making essentially no distinction between these 2 types of errors. You're just saying, how often is it the case that the truth equals the prediction? We can think about it in terms of this table here as follows. Imagine that these are just counts, like you did 1,000 experiments, and so then you record the outcomes, and so those 4 numbers have to add up to 1,000. And so given this table of outcomes, sometimes it's called contingency table, or we'll often call it a confusion matrix. What you could do is you could estimate the probability that of correct by saying, okay, how many times was I correct? So you add those 2 numbers divided by all the cases. So you add those 4 numbers. Okay, so in this case, if you want to measure accuracy, you're just measuring how often is the test correct. So like I said, there's some applications like digital communications where that's exactly what you want. But if you're doing cancer diagnosis, accuracy is really not the metric you want to be looking at. Okay, so here's some other metrics. Precision is what is the probability that the truth is 1 given that you predicted 1. So in this medical situation, you could say, given a positive test, this one, how often is the patient actually sick? Another thing people look at is recall, where you swap the order. So in this case, you say, given that I have a sick patient, how often is the test correct? How often is the test positive? Okay. And as we'll see, you can sort of trade between these. You can make one arbitrarily good by making the other bad. And so you have to be careful in how you balance these 2, and we'll talk about that in a moment. So neither of these on their own are giving you the full story. So there's different ways to try to combine them into a single score. And probably the most common is the F1 score, where you take the inverse of those 2, you average them, and then you inverse that. So this is a harmonic mean of precision and recall. And at the end of the day, now you just have one metric which tells you how good you're doing. And this could be maybe a lot more meaningful than accuracy in some applications. Okay, so these are common in machine learning. Now in medicine, they sometimes use different terminology. So they use sensitivity. This is identical to recall. But then there's specificity. So here, it's given a healthy patient, how often is the test correct, versus given a sick patient, how often is the test correct. Okay, so these are all ways that people measure things. Machine learning, like in scikit-learn, it has easy ways to do this. I don't think scikit-learn talks about these, but you can imagine why they're relevant. So one place where we see this kind of stuff happening is COVID testing, right? Because COVID tests, again, are not perfect, but there's a difference between giving a false positive and a false negative, right? There's ramifications to both, but they're quite different. And so when they design COVID tests, they have to think very carefully about all these issues and weigh things out, and they design the tests in a very particular way so that they get, so that the balance of the types of errors is what they want. Okay, so that's performance metrics for binary classification. Any questions on all these definitions? Okay, so here's how you do this in scikit-learn. It's actually very, very easy. So when you do your cross-validation and you give it a score, typically in the past we'd give it like negative mean squared error, or R squared. Now you can give it any one of these, precision, recall, F1, or accuracy, or you can actually give it a set of scores, all 4 of them, and it will do the cross-validation and measure all those different performances. And then you can extract the results, compute means over the different folds. And just as an example in this breast cancer demo, we have precision, recall, F1, accuracy. They're all in the 90s. And here we even have the standard errors, which we can compute looking across the K different folds, K-fold cross-validation. So the point is it's pretty straightforward to do all this in scikit-learn with those 4 scores. Okay. Okay, now I mentioned before that it's possible to trade off between precision and recall. So this is generally how we do it. So remember that when we do all these linear methods, it's a 2-step procedure. In the first step, so given our test vector X and our trained weights B and W, we compute a score. That's going to be a real number. So 0 typically means like, I really don't know. Positive means I think the label is 1. Negative means I think the label is 0. And, so we talked earlier about quantizing it, but actually when you quantize it, you lose information, right? You lose something about the confidence that is present in Z. So one way to get that confidence is to just plug it into the logistic model, which actually gives you a probability. And this is just a model. It's not a correct probability, but it tells you some guess of what is the probability that y equals 1 given Z. So that's a number between 0 and 1, and that can be very useful. Here I'm calling it a confidence. It's also often referred to as a soft decision. So confidence or soft decision. Now, at the end of the day, though, you need to make a decision. Is this going to be, is y going to be 1 or 0? And so that's when you finally have to convert it to a hard decision. But now, one way that you have some flexibility is essentially where you quantize it. So until now, we focus on quantizing it at z equals 0, which would correspond to a probability of 0.5. Right? We said if z is 0 or larger, we say that we return label 1. If z is less than 0, return the label 0. Or equivalently, if the soft decision was 0.5 or higher, we return 1. And if the soft decision was less than 0.5, we return 0. And in fact, that choice is the right choice if you want to minimize the error rate or maximize accuracy. That's exactly what you want to do. But we said that there are applications where we don't may not care about accuracy directly. We might care about precision and recall. And so here's an example of what happens when this threshold t changes from 0 to 1. Your precision goes up and your recall goes down. In fact, when t is 0, then essentially you're always selecting y hat equals 1. Always. Right? So it's a trivial case. And in that case, your recall is going to be perfect, but your precision is going to be worthless. On the other hand, if you go the opposite way, if you set t all the way to 1, you're always going to be returning a 0. And so in that case, it's flips. And so by adjusting t, you can actually make whatever trade-off you want between these two. You can do the same thing with sensitivity and specificity. So here is specificity goes up, sensitivity goes down. So you can trade off between these just by not really changing your logistic model at all. Everything there is identical. It's just how you use it at the end, how you make those hard decisions. And this T might be very application dependent. And so it's nice that you can design your model, all of that, without thinking about the application. And only at the very end, when you're applying it, you have to make that choice about T. Okay. And so here's another way, similar, very similar in spirit. Oh, yeah.
When you say T equals 0.5 minimize the error rate, that is only for the training data, right? Maybe for the unseen data. And then the threshold would be better for unseen data.
So I guess, it's a good question, exactly what happens with the unseen data. But I would say, like in general, when you have a given objective, which is to maximize accuracy, you usually want to do this both on your training data and on your test data, let's say, right? So now the accuracy, the training accuracy tends to be higher than the test accuracy, usually because you're going to be overfitting to your training. But now if you just measure like how do both of them change with the threshold T, I think you'd see a similar behavior where as T goes to 0.5, you end up getting the best training and the best test, more or less. And so it kind of goes together, training or test works this way. Okay, any other questions on this? All right, so another way you can see a trade-off is you can look at the true positive rate versus the false positive rate. So here's a plot. Slightly different trade-off. So as the threshold goes up, so when the threshold is 0, what happens is you're always going to be selecting y hat equals 1. So both of these are sort of trivially maximized. And then as your threshold goes up, both of them come down to 0. But still, you can see that there's sort of a different behavior. One of them goes down really quick, the other not as quick. And so the way that this is most commonly plotted is you plot what's called the receiver operating characteristic, which is a plot of the false positive rate on the horizontal and the true positive rate. And where you want to be is in the top left corner, where both of those quantities are large. And where you don't want to be is on the bottom right corner, where both of them are, wait, let me see. Sorry, I said that wrong. You want to be up here where your true positive rate is high and your false positive rate is low. So you don't want to be making any false positives, but you want to be making lots of true positives. The worst case is down here, where your true positive rate is low and your false positive rate is high. Okay, so all the way there. So all of these different points in the operating curve correspond to different choices of the threshold T. So as T increases, based on this plot, as t increases, you can see that your true positive rate starts high and goes low. So it starts high and goes low. So that's what happens as t increases. Meanwhile, your false positive rate is moving like that. So by choosing t, you can choose where you are on here. Maybe you want to be here, maybe you want to be here. In many cases, maybe your boss tells you, look, the maximum false positive rate I will tolerate is 0.1. So just give me the best true positive rate for that constraint. And so, you end up drawing something here and you say, okay, this is where my model is. But in some cases, you actually want to measure the performance of your model without someone telling you exactly which threshold to use. So you don't actually know where you're going to be. So you want a threshold independent performance metric. So the way that that's commonly done is you just look at the area under the curve. The area under this curve, like the larger that area is, the better, right? Because as I push this curve closer and closer to that, its area increases. Maximum area is going to be 1. So in general, you see AUCs of less than 1. But this is a nice way to measure the performance of your model that does not require you to make any specific choice on the threshold. So this is very commonly used in literature, this stuff. And how you do this in scikit-learn is pretty straightforward. So in that log reg method, there is a predict probability, which gives you soft outputs on your training samples here. And then with metrics.ROC curve, you can compare the true labels to your predictive probabilities, and it will give you this false positive rate, the true positive rate, and thresholds. So give you basically what you need to plot this. And if you want to compute the area under the curve, you have this metrics.ROC AUC score. Same inputs, and it gives you the actual area under the curve. In this case, it's pretty close to 1, 0.996. Not perfect, but pretty good. Okay, so although we're almost done with the unit, there's a little bit more to talk about, and I think we're done for today. I don't want to hold you any longer, so we'll finish up with this. So yeah, start your studying. Post any questions you have to the discussion boards, or bring them to office hours, and yeah, we'll see you on Monday. Have a nice weekend.